Good morning, students. In the last class, we had studied LCR circuit. We had derived expressions for impedance of an LCR circuit and also the instantaneous current in the circuit. Now, with those points in mind, we shall go to the next point in the chapter. That is, we are today studying the resonance in LCR circuit. So, you are already familiar with the word resonance. I think last year in waves and oscillations, you have studied about resonance. You have also done two experiments in the lab based on resonance phenomenon. One is your sonometer and the other one is resonance air column. Now here we are studying electrical resonance for LCR circuit. So let us write the expressions for current amplitude and impedance which we had derived last time. So we had the expression, derived the expression Im is equals to Vm upon Z. What is Im and what is Vm? Im is the peak value of current and Vm is the peak value of voltage. The peak value is also called as amplitude. So this is current amplitude and this is voltage amplitude. Z is the impedance of LCR circuit, that is opposition of a LCR circuit to the flow of AC. We had derived the expression for impedance as Z is equals to under root sign R square plus XC minus XL whole square. Now let us write the expressions for XC and XL. In the earlier sessions we have written down the expressions for XC and XL. We had also written down the differences between XC and XL, how they depend upon frequency and what are the graphs of XC and XL against frequency. Let us revise the same points once again. Let us write an expression for XC. So we know that XC is given as 1 upon omega C. What is omega? Omega is the angular frequency. What is the formula for omega? Omega is equals to 2 pi nu, where nu is the frequency of AC. So put the value of omega as 2 pi nu. So what will be the value of XC? 1 upon omega C. Omega is 2 pi nu. So it is 1 upon 2 pi nu C. Now let us write an expression for the inductive reactance XL. XL is given as omega L. Put the value of omega. What is omega? 2 pi nu. So what is the value of XL? 2 pi nu L. So if you observe the expressions of XC and XL, you will find that both depend upon the frequency. Now let us show the variation of the reactance with frequency in the form of a graph. On the y-axis, we shall take the reactance, capacitive reactance and inductive reactance. On the x-axis, we shall take the frequency nu. Now observe the two expressions. You can observe that Xc is inversely proportional to nu. What is the meaning? As nu increases, Xc goes on decreasing along a curve like this. This is Xc graph. Now observe the expression for XL. XL is 2 pi nu L. The meaning is XL is directly proportional to frequency. What is the meaning? As frequency increases, XL also increases along a straight line. So this is for XL. Now these two graphs intersect at a common point here at a particular frequency nu 0. So at this frequency nu 0, both the graphs meet at a common point. The meaning is Xc is equals to XL at this particular frequency nu 0, and this frequency is called as resonant frequency. So we shall write the point here. At nu equals to nu 0, that is resonant frequency, Xc is equals to XL. Now let us put Xc equals to XL in the equation of impedance. So if Xc is equals to XL, what will be this difference? Xc minus XL will be equals to 0. Therefore, Z is equals to under root sign R square plus 0. So root of R square is R. So what expression will get? Z is equals to R. So Z equals to R is the minimum value of impedance. The meaning is the impedance becomes minimum. Now if the impedance becomes minimum, what about the current amplitude? You have seen here that current amplitude is inversely proportional to Z. If Z becomes minimum, then the current amplitude becomes maximum. So here current amplitude becomes maximum. So what happens at the resonant frequency? At the resonant frequency, impedance becomes minimum and current amplitude becomes maximum. And this phenomenon we call it as resonance in the LCR circuit. And that particular frequency is called as resonant frequency. Now, one more point you will observe regarding the resonant LCR circuit. We have seen that Z is equals to R. The meaning is it is just a purely resistive circuit because XC and XL they cancel each other. So we are left with only R. So a resonant LCR circuit is a purely resistive circuit. So we had derived the phase relations for a resistive circuit. When we had studied the R circuit, we had seen that for a resistive circuit, voltage and current are in the same phase. So here also a resonant LCR circuit is a resistive circuit. So for a resonant LCR circuit, both current and voltage are in the same phase. There is no phase difference between voltage and current at resonance. Otherwise, for a normal LCR circuit, there is a phase difference phi between voltage and current. But when the circuit is in resonance, there is no phase difference between voltage and current. So this is about the phenomenon of resonance in the LCR circuit. So what is the condition of resonance? Condition of resonance is Xc is equals to XL. Inverse capacitive reactance is equals to inductive reactance. Now, we shall derive an expression for this resonant frequency. Next point. So, resonant frequency nu 0 can be derived based on your condition Xc equals to XL. Say resonant frequency is nu 0. What is the unit of nu 0? The unit of frequency will be Hertz. Now you have the relation omega is equals to 2 pi nu. Let us put the value of nu as nu 0, resonant frequency. So here it will become 2 pi nu 0 and corresponding to nu 0 we shall call the resonant angular frequency as omega 0. So nu 0 is the resonant frequency and omega 0 is the resonant angular frequency. And what will be the unit? Not same as hertz, it is radian per second. So when you express the resonant frequency as omega 0, it is unit is radian per second, and if you express it as nu 0, it will be in hertz. Now we shall derive an expression for the resonant frequency. So we shall start with the condition itself. Very simple. Xc is equals to XL at resonance. Now what we shall do? Put the value of Xc and XL and simplify. So here we have written down the value of Xc. What is Xc? 1 upon omega c. For resonance, omega is omega 0. So what will be Xc at resonance? Xc will be 1 upon omega 0 c. So here I have written Xc as 1 upon omega 0 c. Now find the value of XL. XL is omega L. At resonance, omega is omega 0. So XL will be omega 0 L. So I have put the value of XL as omega 0 L. Now cross multiply and simplify. If you cross multiply, take omega 0 square on one side. Omega 0 into omega 0. Omega 0 square will be 1 upon LC. Now you take square root on both sides. So omega will be nothing but 1 upon root of LC. This is an expression for resonant angular frequency. If you want the resonance frequency, put the value of omega 0. What is omega 0? 2 pi nu 0. So omega 0 is 2 pi nu 0. It is nothing but 1 upon root LC. Take nu 0 on one side. So nu 0 will be 1 upon 2 pi root LC. This is resonant frequency. So this is the derivation for resonant frequency of an LCR circuit. So derivation is very simple. Start with the condition of resonance Xc equals to XL. Put the values of Xc and XL and simplify. You will get an expression for resonant angular frequency. So what are the points we have done now? First is we have defined the phenomenon of resonance in LCR circuit. What is resonance in LCR circuit? At a particular frequency nu 0 called as the resonant frequency, Xc is equals to XL. Therefore, impedance is minimum and current amplitude is maximum. This phenomenon we call it as resonance, and that particular frequency nu 0 is called as resonant frequency. And what is the condition of resonance? Condition of resonance is Xc is equals to XL. The next point we have done is we have derived an expression for resonant frequency. So what the derivation starts with the condition of resonance Xc equals to XL. Put the value of Xc and XL. simplify, you will get an expression for resonant angular frequency as omega 0 is equals to 1 upon root LC, or resonant frequency nu 0 is equals to 1 upon 2 pi root of LC. So all these points are important from your exam point. A question is asked first on write the condition of resonance, that is you have to write this condition. Then derive an expression for resonant frequency is asked for 3 marks. So this derivation is also important. And also 5 marks problems are based on the calculation of resonant frequency. So in the problem, L and C values will be given. You have to find out the resonant frequency. So problems are based on this derivation. So it is important from your exam point. Now the next point we shall study is we shall draw a resonance curve for LCR circuit. The resonance curve is a graph of current amplitude Im on y-axis and the angular frequency omega on x-axis. You will see that the graph is a curve like this. So this is the peak point of the curve and it corresponds to the maximum value of current amplitude. So we shall denote the maximum value of current amplitude as Im max. Max stands for the maximum value of Im. Now just now we have studied the phenomenon of resonance. We have seen that at resonant frequency omega 0, the current amplitude Im is maximum. Therefore, the frequency corresponding to Im max is nothing but your resonant angular frequency omega 0. Now, we shall take a lower value of Im max. That is, we shall divide Im max upon root 2. The value will decrease. Let us say this is the point corresponding to Im max divided by root 2. Now, corresponding to this value, how many values of angular frequency you get? You will get 2 values of angular frequency omega 1 and omega 2 corresponding to Im max upon root 2. We shall find out the difference between omega 1 and omega 2. So that difference omega 1 minus omega 2 is called as the bandwidth of the resonance curve. Now the quality of the resonance that is defined in terms of a quality factor Q. So let us define the quality factor. The quality factor Q is defined as the ratio of resonant frequency to the bandwidth. Resonant frequency is omega 0 and the bandwidth is omega 1 minus omega 2. Therefore, Q is equals to omega 0 divided by omega 1 minus omega 2. Now, to have a sharp resonance, Q value should be large. So, when is Q value large? Q value is large if the denominator is small. That is, the bandwidth is small. And if the bandwidth is small, the curve becomes very sharp like this. The meaning is the Q value measures the sharpness of the resonance curve. Also, the sharpness of the curve depends upon the value of resistance in the LCR circuit. So, this particular curve is drawn for a small value of resistance. What will happen if you increase the value of resistance? So, you know, as you increase the resistance, current will decrease. So, for a large value of R, the value of Im max will decrease. And also, the curve becomes flat like this. So, this is a sharp curve, this is a flat curve. So, what do you observe? As you increase R, the sharpness of the curve decreases. Now, we shall find out the value of bandwidth. So, the bandwidth from the graph is shown to be R upon L. So, we shall put the value of bandwidth and simplify. So, Q is equals to omega 0 as it is upon omega 1 minus omega 2. So, what is the value of the bandwidth? It is R upon L. So, substitute here as R upon L. Simplify. L will come to the numerator. So, it is omega 0 L upon R. Now, just now for resonance, we have seen that the condition is Xc is equals to XL. The meaning is 1 upon omega 0 C is equals to omega 0 L. So for omega 0 L, we shall put the value as 1 upon omega 0 C. So this is equals to 1 upon omega 0 C and R as it is. So you got two expressions for Q value. One is omega 0 L upon R and it is same as 1 upon omega 0 C into R. We can find here another expression for Q. What we shall do is, we shall put the value of omega 0. So just now we have derived an expression for resonant frequency omega 0 as it is equals to 1 upon root LC. We shall substitute this value and simplify. So for omega 0, I have written the value as 1 upon root LC, 1 and L upon R as it is. Then this is equals to 1 upon root LC. For L, I shall split it into root L into root L divided by R. You can simplify. 1 root L gets cancelled. So what you are left with? You are left with 1 upon R into root of L upon C. So this is yet another expression for Q value. So we have got three expressions for Q value. What are those? Q value is equals to omega 0 L upon R. It is same as 1 upon omega 0 C into R. It is same as 1 upon R into root of L upon C. So in the exam, if a problem is asked to find the resonant frequency or if it is asked to find out the Q value, then you have to use any one of these three expressions. So value will remain the same. And remember that Q is just a number, it has no unit. Now, just now I told you for a sharp resonance, you should have a large value of Q. So when is Q large? It depends upon the values of L, R and C. L is in the numerator, R and C in the denominator. So Q is large if numerator is large and denominator is small. The meaning is Q is large if L is large and R is small and C is also small. So now these are the conditions for the large value of Q. Now I will tell you one very interesting use of this resonant LCR circuit. It is used in the receivers of radio and television to tune to a desirable frequency. Now the antenna receives different signals of different frequencies. Suppose you want to hear to a particular radio station or you want to see a particular channel, then you need to receive that particular frequency in the receiver. So for that, the resonant frequency of the tuning circuit is made equal to the frequency of that signal. Then resonance happens, the current amplitude will be maximum and that particular frequency is received in the receiver. So this is one very interesting use of the resonant LCR circuit. Now let us summarize the points we have studied now. First is we have drawn the resonance curve. It is a graph of Im against omega. You get a curve like this. Then the maximum value of the amplitude is for resonant frequency omega 0. Then for Im max upon root 2, you get two values omega 1 and omega 2. You take the difference between them, that is called as the bandwidth. Then how do you define the quality factor? The quality factor is defined as the ratio of resonant frequency to the bandwidth. Also we have seen that quality factors measures the sharpness of the resonance curve. Also the sharpness depends upon the value of R. As R increases, the sharpness decreases. Then we have substituted the value of bandwidth as R upon L. We got three expressions for Q value. Q value is omega 0 L upon R or 1 upon omega 0 C into R, or it is same as 1 upon R into root of L upon C. Also we have studied one very interesting use of resonant LCR circuit. We use it in the receivers of radio and television to tune to a desirable frequency. So this is all for today's session. Thank you.